Yes.
But we try and give it a go and then the calibrate is
Okay.
So
Or you can do like I said, maybe because that one it's what? It has to be contacted or is it laser?
It has to be contacted.
Contact, no? So maybe you can, anyway, maybe not for this one, okay. But I mean to be commercial, yeah, I don't think that's proper. So maybe you can find very thin layer of whatever material that actually transmit the things. And then you put it there, so then I don't feel something poking my finger, or get hurt, or get injured, so it's not safe actually. Right? Because there is some sharp point. Yes, go ahead. Group? One. Okay, go. Yes, sir.
So for the problem identification, rubber springs are often damaged because the rubber members cannot maintain a consistent traffic light. So most of them cut too deep or too shallow, which provides the slope most of the traffic. So we know that they are using the traction and line, which do not have the depth control features. So that is the root cause. So that's why we come up with the idea of EZTap. So EZTap is a 3D integrated device with a built-in depth light and also fixed cutting angle of 30 degrees. So all of this is intended to ensure uniform tapping while minimizing trade damage. Okay, so as you can see, this is the standards that must be adhered from the ISO. So for EZTap, it has achieved all of the user needs. So we can see here like accuracy, practicality, operation, and affordability. It has achieved it. However, for these two products, there is limitation in terms of practicality and affordability. Okay, so this is the functioning diagram of EZTap. So this is the casing. So the casing is equipped with 30-degree blade. So this is the roller which stops the movement, and then this is the motor casing which encloses the motor and the blade, and also the handle for the ease of handling of the device. So here you can see the system architecture focuses on 3 points, which is cutting system, user assistance system, and also practical and efficient operation. So all of this is intended to prevent overcutting, to protect the build, easy to use operating system, and also ergonomic design for tappers to reduce discomfort. Okay, so for the design specification, the design has to protect the tapeworm from any damage and also maintain consistent cutting guide. So this can be achieved by fixed blade depth and also fixed blade angle of 30 degrees. So the next one, in order to overcome the low effort cutting operation, a minimum force must be applied by the rubber tappers, which can be overcome by 50 Newton cutting force, which is then be scaled down to 5 Newton by 10. Okay, the last one, in order to get a very smooth performance design and also minimize softness, it must cause less shaking on hand. So that's why the RMS vibration acceleration should be less than 2.5 meter per second square.
Okay, for design analysis, we're going to start first with motor specifications. The engineering target is to achieve 5 Newton of cutting force. So the design question is how much power does the motor need to produce a 5 Newton cutting force? So first of all, we in the previous presentation, we set the cutting force is to be 50, but due to the availability of the motor specification, we reduce it by 10. So we use 5 Newton of the cutting force instead. So we recalculate the top step down, which is we get 0.25. Also we calculate for the power calculation, and we got about approximate 9 watts of power output needed. So this is our motor specification. We use a DC current 12 volts with 14.4 watts of power output with a cutting speed of 333 RPM. Okay, so next for battery capacity, we want to identify how much is the battery capacity needed. Ensure that the battery can power up the DC motor safely. So we use a DC to DC buck converter, which we step down the voltage. So we calculate first the motor current requirement. Where we get the normal operating power as well as the stock power, and we also calculate the converter current requirements, which we choose, which we use our current of 10 ampere, and we get a safety margins about 2.3 times from its peak current. So we estimate that the operating hours is to be 1 hour based on these calculations, and the battery specifications is 10 amperes with 21 volts. We step it down by 12 anti-12 by using a buck converter. Lastly, vibrations. We want to evaluate how much cushion thickness is needed to cater the vibrations from the cutting force. So first we calculate the vibrations, which we are from the RPM of the motor, which we get 5.5 Hz, as well as we calculate the isolation target and where we found the natural frequency of 3.89 Hz and also the required stiffness of 1194.78 Newton per meter square. And also from the information that we get earlier, so we calculate and we use it to calculate the contact area, which we get 0.00071 meter square, and the final thickness is 0.6 centimeter. So the handle specification, we choose a silicon form with a final thickness of 0.6. So for prototyping process, for KOE, we use solid wood printed. We use PET filaments for blade manufacturing. We cut the blade to 5 cm. We do some grouting on bend section and also drilling. Also for motor and leg setup, we put inside the casing. We attach the blade with the shaft coupler, so the bearing to reduce the friction. As well as for roller installation, we put in the shaft. And where we rent the handle with a silicone foam. Also we power up the motor by using a battery with a buck converter.
So the next one is about the test cut. We achieve all four engineering targets, which is the blade depth, cutting angle, cutting force, and the vibrations. So for the first one, we want to measure what is the depth of our machine could operate. So we do a real tapping test on the tree trunk using the prototype. This is our prototype, and we measure the remove bar using the vernier caliber. And then the next one, from the cutting line, we calculate the cutting angle. And this is the result. We get the buck thickness of 1.8 mm, and we get the angle of the degree. So this angle we get from our smartphone applications. And then the next one is we want to measure whether our product could achieve 5 Newton cutting force, which is a scale down. And then how we do that is we connect a 0.5 kg water filled bottle, and if the blade can lift the things, then it defines our cutting force. So from the result, we able to get lift the water filled bottle up until 1 kg, which equivalent to 9.8 cutting force, but we fail at the 15 cutting force. And then that means our maximum cutting force is up until 9.81. And the next one is we want to measure whether our product is good in terms of sturdy design. So we attach the smartphone with a vibration measurement application to the handle. So we want to calculate what is the vibration. So over here, 2.5 is our set point, and from the result we get everything is below 2.5, which means our product is less in terms of vibration. Socio-environmental impact of EZTap. We know the problem of incorrect tapping chemistries, which lead to shrinking smallholder productivity, and we also know that the healthy tree can be tapped up to 25 years, but the one that is damaged may need 4 to 5 years to recover. So we will bring you two of the benefit, which is the first one, because we embedded in the dive guide plus fixed angle, so we have a safer cut, which lead to healthy trees and longer lifespan. And because our product mainly use tree plating, and only the blade is made from the steel, so we have fewer needs of steel manufacturing. So this is aligned with SDG 15, which is live life on land, and SDG 9, which is industry, innovation, and infrastructure. And the next one is economic impact. So what is at stake? We know that our production is dropped from 1 million to over 400,000 plants, and then this is because of the productivity loss from damaged trees plus reduced carbon quality consistency. But with our product, we can assure you that we can have a fewer damaged tree, fewer unproductive years, and because our product is beginner friendly, so it requires lower training costs. So because of this, we can achieve the SDG 8, decent work and economic growth in our venture. And then the next one is stakeholder consideration. So stakeholder is basically the person that is affected by our product, and it determines whether our product is a seed or not. So our primary user is smallholder applicators, and then we have this. We also will benefit these three categories, which is the smallholder association, rubber processor buyers, and local national planting partners. I mean. Regulatory analysis. So because our product is a handheld cutting device, so we need to check whether our product is safe. We need to check whether our product can resist with the outdoor condition, the UV, the rain, heat, and mud. And we want our product to have a very good mechanical strength, so it can have a longer life cycle. And then we need to check whether our product is consistent in terms of depth or angle performance. And also, of course, we need to check whether our product is good, standardized within the ISO. I think that's all from us.
So, we need to check. Did you do the check? Huh? Did you pass all the checks?
Yes.
I need to check. I don't know if you check or not. So you check. Alright. I'm gonna start differently this time. What is the blade? Yeah. That's the blade? Hey, how is that safe? The blade is exposed like that. You know, do you have any cap to protect it when it's not working? Like this guy, he's moving like that, you know, and then turn and then oop, you get the blade, you know. This one, not very safe like that. Yeah. No, you can just make a cap when it is not used. When it is used, okay, then you remove the cap when it is at the tree. Okay, so that's why. Because you mentioned there the blade, blah blah blah. So I feel that I want to see that one.
We can open the blade, so it's not directly attached. We can, we can just attach this blade.
Oh, that also probably, but again, if you attach or keep, but it should be protected like that, because that's actually the most harmful part, right? There's nothing else actually can sharp or something like that, right? So maybe that one you need, but even like, I mean, attach it and put it during the use and stuff. So better usually like they do this when it is captured and they cover it, you know, when it is not used. And use it, then you just remove it, then he knows that. Okay, so that's what I want to ask this time differently about the thing. I think your load is nice. You can prove it on that side. Your design spec, just quickly, but I think I'm happy with that. So you have this angle. Okay, why did you scale down 50 Newton to 5 Newton? What's the big difference?
Because of when you calculate the first needed to cut 50 Newton is the motor need to cut 50 Newton is so high. So what is
What is the calculation? Did you do for 50 Newton?
So for this, at first we calculate the 50 Newton cutting force.
So
So
you
the
got
top needed is 2.5 Newton meter. So the motor specs that we refine is only that produce about 0.25 to 0.8 something like that. So
that one very expensive.
this one, if you want to use this, the price is about 180. So it's
100?
180 plus. So
180 plus, and that's too much.
there's too much. Where our motor is just 30 ringgit. The budget is the limitation.
No, see, sometimes guys, you're so cheap. I'm sorry to say that. Okay, because your product looks very nice. It can be actually almost used. But now with that one, I cannot use it, right? Because it doesn't do the job for the real thing. Just because of 50 ringgit. Difference of 100 ringgit, right?
It's about 100.
100 ringgit. No, honestly, usually we do scale when it is like that, you know. There is one, I cannot, so I have to make it small. But you guys, it's the same shape, everything will be the same like this, right? Except the motor. Yeah. So that's actually a big no for me. Okay? You shouldn't go for that, you should come to ask me, I'll give you some money. But now, I'm not your supervisor, but still I will give you some money. Right? But then you will write something that I will take 20% the share of. Anyway, no, it's kind of nice, your things. Your calculation also, you start with the 50 Newton, engineering target, then you put it, then you found the power and stuff. That's how the design analysis should be done. Can I check some other components to make sure that it is right? This one is for?
This one is for previous powers that we need.
Oh, the big one.
Yeah, the big one.
Okay, next one. Because I think I saw some that not right. But let's see. So this one to check the
battery capacity.
The battery capacity.
To power up the motor.
Okay, how do we calculate that one?
This one.
So you have the motor, which needs this 12 volt, because you found your motor already, right?
Yeah.
So you pick that motor that it has that torque, that thing, so it needs this volt ampere, so you get 14.
So the spec of the motor, actually the peak current, the maximum current when the brake is jammed or something like that, it's about 4.3 ampere. So that's the max one. So we find the battery that we use 10 ampere instead of 4.3 because we want to have a safety margins.
Okay.
So that, yeah.
Right, acceptable. Next one.
This one.
Let's say the vibration of this one too. So
This
the
one
battery
is
also.
operating.
Okay. The operating time, this you get
1 hour.
1 hour. Is that a target? Not engineering target.
Actually, for the unlimited engineering target. But
So why?
hour, we can cut from for 1 hour we can cut 100 trees using this prototype.
Yeah, but why that 1 hour? I mean, here I don't see. So your battery will live for 1 hour.
Yes.
The battery will allow you to operate with this for 1 hour.
We just put the calculation instead.
So after 1 hour, we can charge it.
Understood? But why you do this? Is this a target?
But extra information.
That's confusion.
Oh.
Because your targets, does he need to increase the, I don't know, the production, operation, whatever it is? In your engineering target? Is it important from the user perspective? For him, just the depth, the angle, the force, this, it doesn't need to do 100 trees or 200 or whatever. No. This kind of thing. Anyway, like I said, this is as if it is in another target. So you want to use for 1 hour, 2 hours, 4 hours, whatever. Okay? Quickly, this one here, the vibration, yeah. So here, what is that speed and mass?
This one is from the motor, 3 RPM.
So the vibration comes from the motor only.
Yes. We calculate, and then we get 5.5. And then this one is total is the force from the machine itself and the cutting force. Combine it to find the mass. The mass, which is 2 kg. Actually, our real prototype is not 1.5 kilograms. It's about 1.3. So this one is just our engineering targets.
Well, just I don't understand this calculation here for the vibration. So you get the frequency there.
This one is actually for pushing this one.
So the target is to reduce below the 2.5 meter per second square. Don't have acceleration.
Okay.
So that's why for the engineering target, we have to find the distance of the cushion needed to overcome this, to make it below 2.5, which is
Now, see, that's why I said from the beginning I want to see this one. Like I told you, the vibration. The other, I started with the good one. So here you should start from your 2.5. You want to achieve 2.5, so you have to think maybe the mass, you will play with the mass. I don't know what is the variable that you need here to achieve that one. Similar to what you did before with the other component. Because here, for the vibration, what are you doing here? Are you trying to reduce the vibration?
so 353 RPM.
No, but that one you cannot play with it. That's from the motor already, right? Which you need the spec already, so you cannot change that one. Can you? Since you do the spec. So what are you doing? What is the component related to the vibrations? When you say stiffness of what?
The silicon.
So you use the silicon. You try to design the silicon.
For the vibration.
Okay. then probably it's okay then, right? Go back.
We do this calculation actually for to find the parameters for the nets, to find the contact area.
We get the KOE here.
And then we use it.
Then over here to get the KOE.
Okay, but given that way, I want to see now from now, how do you know that you achieved the 2.5?
The validation.
No, not the validation. I mean, because you see, you put it as a target. Where did you use it?
So the one is ISO from regulation. So we make it as our set our limit.
No, you should do like the guys, you know, the trimmer. Because they have the same, that's their 4. So you put the 4, your target, that acceleration, how it is involved with your, I don't know, the vibration or your frequency and stuff. And then you come, and then you, at the end, you find, maybe from the stiffness, and then you find the thickness for your thing. But you should start from that, because what we did now is verification, the other type of design that we don't want to repeat. You have your parameter, you do the calculation, it is 2, oh, it's less than 2.5, then it's okay. You know, that's not what I want. I want you to start from the 2.5 and then you find the thickness of the thing. I don't have to check now because I know I started from there, I found this, and it achieved already. You understand the two types different of design which one I explained. So if you do this one like that one, then it's very nice. Your project completely nice. Okay? Just we adjust maybe that calculation. I'm not sure if it will affect. You find different results for your thing, then you can change it because you need only the thickness of this. Where do you put that one? The outside one. And you can actually update with your prototype. If you need more thickness, just add another layer or something like that. You need less remove. Okay? Alright, good job.
Wait. Question from.
But still, I'm not happy with one thing, the scale. Everyone goes for scale and scale. This one doesn't need scale.
Okay, my question regarding your engineering design specification. So there are 3 design specifications. Based on your engineering target, based on your engineering target, could you please justify the design analysis for each? Because I couldn't see the relation you target with your design analysis. Could you justify? Should it be one by one?
The second one you showed, like that's for the motor, right? The force that you showed. But the first one, if you can show the first one, the depth and the pattern where it was used in your calculation.
Yeah, the depth. Maybe show the design analysis for depth.
The validation is there, yes, I can see, but your design analysis.
You know? Okay, let me make it simpler for you. You use it 50 Newton here, right?
Yes.
Then you brought it down to 5 Newton. You use it that one, you calculate it, and then you find the motor power, blah, 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 right? So that's the flow. She wants to see for your other engineering target, like the depth of 1.8. The pattern angle 8. Where did you use that to find maybe the blade or I don't know, whatever characteristic of it?
Oh, actually, it does not even change because this is the real data obtained from the LDF. They use 1.4 to 1.8 millimeter black depth in order to protect the cambium.
If we have a tree, if it is at 1.8, it will raise the cambium. We don't want our
Which
plate.
design?
Yes, but still, you have to design that. I know you don't need, but I could blade now, right? So how do you know it is between 1.4 to 1.8?
Yeah, the difference between roller and the knife should somehow should create the design analysis.
Even though it will be straight, let's say, I'll make it simple, I'm not sure your design, but this is, let's say, my blade, right? So I will say my blade is actually in 2 positions. I put one position, 1.4, then it will go. Then, if I want to go 1.8, then the other position, then 1.8. Then I satisfy. I don't need to do any design. Just I take the blade and I put the two lenses like they did with the thing before, like 4 to 6. So they make it here, it is short 4. If they extend it, then it is 6. That's it. They do 2 segments, 3 segments, 5. Yours, it has to be shown. You cannot put a design here and then you don't put any part related to that. Otherwise, it's not engineering part of that. No, don't put it there.
And the last one in RMS vibration acceleration, which one? Which design is it that you can improve based on your engineering target?
No, the
That
last
one
one.
we have a push.
The last one, yeah.
The last one.
Pushing fitness.
Which one? Vibration.
Yeah, this one.
This one.
Find the thickness of it.
2.5. What is the relation with the RMS vibration?
It is
2.5?
when we relation.
No, relation.
No.
Yes.
The analysis, you get the frequency, how from that frequency or from whatever, the thickness here is related to that. Because this is your analysis, you start, go to the previous slide. You started with that one. Like I told you, you should start from the 4, the 2.5, let's say, and then reverse. But you have to, because here you get the stiffness, or you get the frequency or whatever, then go to the next slide, then you give us a thickness. What is the thickness is related to that the previous calculation? To say that this reduced that frequency.
Basically the acceleration, not for this acceleration for the K, that one when we use 5.5 Hz is because from this prototype the only vibration introduced is because of the motor.
Okay.
So that one we use 5.5. But for the RMS is the vibration acceleration, which is caused by the when we cut the tree, it introduces some resistance. When blade touch the tree, contact with the tree, so it introduces vibration and introduce resistance. So it causes our hand go back and forth. So that's why introduce, because of the change direction, introduce acceleration. So 2.5 come from the acceleration this one. So when we put this, so it can. So after when we validate, so this one for validation.
Oh, no. That's two different things. The question which is valid is how that one is affected. So I thought that from your frequency you should get similar, like I said, to the grass trimmer. Right? They started from that and they found the gel, that they need this K or whatever, and from that, then they found the thickness. Right? Then it makes sense. So if they started from the acceleration, they end up by the thickness. You should be the same. That's the thickness that will kind of reduce whatever, then you should start from there and then get me what is the gel or the thickness of this thing. But here, there's no need. Yeah, go ahead.
Because previous slide, you mentioned 5.5, your engineering target is vibration less than 5.5 Hz. But I can see in your design spec, there's no values your vibration 5.5. Okay?
But actually, it should be related to the last one. Just you use one thing, but there's no link. So if you get the 2.5 to be linked to that frequency and that frequency or stiffness or whatever, link it to the thickness, then you're done. But currently it's not. So like I said, we check similar to the other guys that they did. Very similar. We check with that group and we try to get the same flow. Then you fulfill the last one. The first one is not fulfilled, but it should be like fulfilled like easily. Because right now, how do you know it is?
The difference between the rotor and the blade.
Yes.
1.8.
Well, that's it. So then you say that one, you have another slide or whatever you look for. That this is the thing, I need this 1.4, so I'm going to design this gap to be 1.4. That's it. So every time I put that one, cannot be more. Right? So then I'm achieving 1.4. Because some parameters don't get into calculation based on the geometry.
Okay.
Okay, but you have to put, if you get a target, then you have to show that it's related to one of the geometry physics of your prototype. Okay. Alright, thank you.